Thank you, Christoph. By the way, the same convincing took place also with René Janssen just a couple of years earlier in Santa Barbara when he joined us in 1992 in Santa Barbara. And I'm very happy to see that actually many discussions we had at that time in 1990s are still going on. And today I was asking this question to René. Still PCBM is apparently having its king's place also in perovskite solar cells. And just an anecdote how this PCBM came into game at all was that I was looking for an electron acceptor, and then I went to Fred Woodle and asked Fred, give me a good electron acceptor. And he took this powder, which is brownish black, and he said, take it, this is good. It takes up to 6 electrons. So this was the birth hour of C60. And then, but it's not so good soluble, this animal, even though we both liked it. I mean, René is also a football fan, and myself. So it looks like an exact football norm of FIFA. And then, however, it's not soluble. And then K.S. Hummelen, who is now in Groningen, came and made this functionalization. And actually, K.S. did not make PCBM for this purpose. It was a precursor for a purpose which was the so-called HIV virus inhibition project. This was a biochemical project, biomedical project, and this PCBM he had to do in large scale so that he can functionalize much more complicated fullerenes out of it. And he said, I mean, he told me several times later on, he said, this is a bloody physicist, he doesn't know anything about this chemistry anyway, so he gave me this, what he has in larger amount. So this was the birth hour of this PCBM. So if some younger generation wonders why this strange molecule is still on the way, but it was indeed a great luck that we have this interesting molecule. So one important thing is I was also impressed on the detail level of this afternoon here today. I was feeling that I was looking like with a microscope into these problems. So I will now take the liberty, this is last talk, so I will now zoom out. So it's not only microscope, it's not only visibility, it will be maybe going to a satellite view. And sometimes it's important. I mean, young scientists often dig themselves into a detail, and I always say they see only the trees and never see the forest. So it's sometimes important to get the orientation also by looking from above. So what you see here is something which we recently did. This is a nano-biocatalyst. These are graphene layers which are functionalized with biological enzymes, which do indeed in a wet condition, if you bubble the system with CO2, these enzymes transform carbon dioxide all the way, all 3 enzymes together, to methanol. And these are without any NADH or any kind of biochemical fuels working electrocatalytic or bioelectrocatalysis. So now it should work with this, definitely not. This one doesn't work.
Click on the PowerPoint slides.
Yes. So the first important thing I really want to draw your attention is these sustainable development goals. These are new, and many people don't even know about it. Everybody knows 1948, the Human Rights Declaration of United Nations, but nobody knows that this happened. So this is after 1948, the first time United Nations gave some projective goals. So if you have never read this, please do that. It's highly interesting. And one of them, of course, is number 7, affordable and clean energy. So we are going to talk now on that level. Of course, solar energy. What else? It would be just 2-3 points here on this map if you would plot the so-called oil places where the oil is recovered from the earth. However, solar energy is everywhere, more or less. But this is the most democratic form of energy. And Africa's future depends on solar energy. And I was always highly interested in Africa. We went several times there. Some of you recognize here Dieter Meissner, of course, Ole Inganes, and many people. We worked in Africa. Carlo Tagliani went, actually already, he passed away. So important parameter was, I said, it should be a kind of a network of solar energy for scientists in Africa, for Africa. And this was created, and SOLE was created in February 2011. I want to put it here because you are a solar energy center here. So this network exists since 10 years now, and they are pretty active in many ways. So now if we look to Europe, just from the European point of view, the southern European countries, they are the most solar rich countries. And as you know, we also have economical problems with these countries, exactly. So I wrote an article at that time, it made create some noise. It was completely translated in Greece, and it was also published Greek and published in Greece. Why don't we send solar panels to Greece instead of money? Because money is mostly used to compensate the losses of these banks, but the solar energy, and this would be 130 gigawatt of solar energy panels. With this money, we already sent to Greece. Greece would be probably the most biggest solar exporter in the world. And I also think that the solar energy has something to do with peace. World peace is getting more and more important, and the young generation will feel the importance even more and more. If you have a terroristic attack, probably it will be on nuclear plants or in oil plants or oil refineries or somewhere, but I don't think that any stupid terrorist will come and blow up a solar panel. And if it did, it would have no effect whatsoever in the great network of solar panels. So in that sense, intrinsically, it is a world peace story. And we made this conference in Istanbul. Some of you, of course, remember that. And interestingly enough, solar energy has also a history. Many people think that solar energy started today or 10 years ago or 20 years ago. No. John Perlin wrote this book, From Space to Earth, The History of Solar Electricity. John Perlin is in Santa Barbara. He's a writer. He's not a physicist. He's not a chemist. He's an author. And he made this wonderful book. If you are interested, please find that. For example, he digged out that 1878, this is exactly the World Exhibition in Paris. This animal was also exhibited there. Everybody remembers this Eiffel Tower. When you go there, you make always a photo in front of the Eiffel Tower. At the same exhibition, this was the solar concentrator, basically running a perfect steam engine. And for example, this 1892, he digged out all these things. It's amazing. This is water heater. This is solar thermal, was already a market in 1892. And I like very much actually this Frank Schumann. He's originally from, I believe, from this part of Germany, his family, and he went there and created for agricultural purposes solar panels, which indeed heat up and run a steam engine which pumps water for irrigation. This was 1907. So it's indeed more than 100 years ago. And he made even some plans. So today we are talking about this Desert Tech project in North Africa and think that we have discovered the wheel. No, it is very old. And if you go for these concentrators today, of course, with parabolic systems, you can get much better concentration factors. And slowly US military is now moving more and more to this, what we call Stirling engines. So if you focus the beam and gets a very high temperature, you can run the Stirling engines. These are not combustion engines, these are more or less the Carnot engines in practice. And of course, everybody knows these big towers. Some people say these big investments are not so practical. We will see what will turn out. But I was recently, and before Corona, I was actually in Negev, and they have an enormous activity there. They put all kinds of photovoltaics, and then they put all the solar thermal. They put this big tower, high temperature for concentrators. They put all of them together, and they are testing and real facility. And this is, as you can see, really miles and great investment there. So, of course, photovoltaic, of course, Fuller, Chapman, and Pearson. And I really am very upset that none of them got the Nobel Prize, and basically they are passed. And if somebody dies, you don't get the Nobel Prize. So I believe Nobel Committee should indeed think about these renewable energies a little bit more than maybe after crying when the people are dead. So this is the logic of this book of John Perlin. When John Perlin says from space to Earth, it says actually indeed in space, every satellite is powered by solar energy. So now it's coming back to Earth and making, hopefully, an interesting development in the world. So this, of course, everybody knows. I just wanted to draw, it took us around 20 years. If you calculate even former in Santa Barbara days, even 30 years to get to this level of 15–20%. So it is really, really heavy work and time. Many hundreds of people work on that. And there are these dots here. These are the perovskites, and they managed to get to these numbers within 2 years, 3 years. So this is unfair, I have to say that. I mean, everybody works in organic solar cells are indeed pissed off on that, because there is a material class which can be done in a kitchen and gives 18% solar cells immediately. So, but organic solar cells have their advantages too. I will come to this. These are inks, you know, all the way, of course. And for example, for me, it's very interesting that we can do really very thin solar cells. They are so thin that you can more or less cover, and you can stretch it. And this was the Kalten Bruno and Matthew White. Matthew White is now in Vermont, professor himself. He went back to US. Martin is now himself a professor in Linz. So why it is so important when it's so thin? Because of the weight. And if you publish this diagram, as you see in the left on the Y axis, you see watt per gram. And you will say why? Because watt per area would be the efficiency of the solar cell. Why would you plot it watt per gram? In that time, actually, we didn't think about this too much. But after this paper was published, telephone was ringing nearly all week, because the Air Force, US Air Force, NASA, ESA, everybody who works in space agencies get this news, because the weight is the single most expensive item if you transport some equipment to the orbit. So therefore, weight is an important issue. And you can see we can beat here silicon by orders of magnitude. Of course, perovskites are even better. Now you see this young gentleman here, and this other young gentleman. This was me for 20 years and 20 kilo ago. And this young gentleman is still young, I have to say that. And this was in the early days when we created the company Konarka, and joining the forces with the Konarka in Massachusetts and Lowell. And this is interesting. This web I have seen today is still going on, this great printing technologies. And I've also told today by Christoph, still PhD. I mean, PhD seems to be really another magic material. We bumped into it, but I hope it will be now using other materials too. I draw your attention because I didn't see any activity on textiles. So you can also take real textiles and make coaxial fiber solar cells. This could be an interesting issue for detectors, light emitting diodes directly on the fiber and not on the web. What also interesting is this paper. I mean, this was a very crazy idea of Arve Tübler. We were discussing about what is this best substrate. Many years. This is polyethylene terephthalate, but there were all kinds of suggestions came. And Arve Tübler said, hey, wait a minute, Sarah, why don't we use paper? I mean, we are printing on paper since around 2000 years. So we know how to print on paper. We should use paper to make a solar cell. And we did paper solar cells. And this was a European project. It works. It really works. However, paper is not an easy material. I have to say that, but it works. Again, to this perovskite, I want to bring your attention to one or two things. Basically, David Mitzi, I know him from IBM labs, and David was working 30 years on perovskites. And I'm really surprised that he didn't bump into these materials and what we call ionic perovskite. So you see, David Mitzi classifies perovskites in 3 different forms: the covalent organic inorganic hybrids. These are the ionic. This is what we are talking about when we talk perovskite solar cells. And there are also these van der Waals type perovskite, basically organic inorganic hybrid systems. So everybody knows this. I don't want to go too much detail. We immediately used, of course, perovskite in our standard organic solar cell configuration. Again, PCBM on the left, P.PSS on the right. So this works, and it gives you indeed in our kitchen without anybody getting high schooling. Every visitor can get 10, 12%, 13% immediately. So this was indeed a good surprise. I didn't see up to now also here a little bit I want to bring to your attention. I just edited this slide when I was listening to the afternoon. We always use this PT-CDI. This is so Perlane D-emit derivative. And this is something which really stabilizes perovskite. So I didn't see it was used a lot. So I just wanted to show it this in that paper. It gives quite some stabilization also. So without PT-CDI, it's less stable, at least in our hands. And you can also make this stretching materials, very thin layers, etc. But now comes the point. We in our institute moves more and more from perovskite solar cells to perovskite emitters, light emission. And they can be very good light emitters. And if you confine them in, for example, ALOX, etc., you can get light emission with an enormous efficiency. Photoluminescence quantum yield, I will show you in a minute, can go way above 95%. 95% of all photons getting absorbed get out as a light. So this is something. So this, for example, was a very nice work with Ayşe Turak. She's in Canada, in McMaster. She uses D-block copolymer, and now, of course, René has the systems in his institute, D-block copolymers create always these micelles. And if you have an hydrophobic outside and hydrophilic inside, you can make in these small nano cavities perovskite nanoparticles. This is a nice cavity. The good point is, I mean, it's indeed quite some size distribution uniformity, because this micelles, the size of this micelle is given by the length of these 2 components. So this paper also I like very much because this was a very unique synthesis method. And then we moved more and more into these nanoparticles, perovskite nanoparticles. And the best materials we have up to now are this peptide and bioligands stabilizing the system. And it's amazing. I mean, you get efficiencies. This peptide ligands, they go way beyond 95, 98% quantum yield in photoluminescence. So this is, at least for my experience in whole physics life, I've not seen something like this in my whole life. I mean, this is amazing and stable. For example, this arginine, lysine, amino acids, we can use many of them as, and Anna finished PhD now. She's from Czech in Brno University of Technology. She's working there now with Kitech. She was as a student in our lab a long time, and so this was her work together with Yolanda Salinas. It's really nice work. However, it doesn't end there. So what do we do now with the solar energy? If we create photovoltaic or whatever energy from sun, we have a problem. Many of you know it, of course. I will repeat it here for you. If you create the energy or convert the energy from sun, you have to consume it. But consumption might be a little bit later, so you have to store it on the spot. Or it must be somewhere else, so you have to transport it on a different way. So this transportable fuel created by solar energy conversion is the holy grail right now. And if you look at this definition, you can immediately say this is hydrogen. I know hydrogen is the biggest boom today in Europe, in the world. But hydrogen, we will see. I mean, hydrogen is as a precursor very good, but as a vector, I don't know. Some people say we should use batteries. Yes, batteries are interesting, and these are the pictures from the book of a paper of Gruner, George. So, but in the end, batteries, you see this watt-hours per kilogram. Even the best batteries, we have around, let's say, 80 watt-hours per kilogram. One of these 1 liter of gasoline has around 20 kilowatt-hours per kilogram. So you have to see the differences. The energy density is much, much less. Can we solve this problem? Yes. As you know, there are the so-called redox flow battery systems. So you don't charge the battery on the gasoline station, but you just take an anolyte or catholyte and change on the gasoline station. You can even pump these things in and out of your car. And these kinds of redox flow batteries can be quite interesting. And I know many people are working in this field in Germany, but this CellCube is, for example, a company which is now purchased by the Canadians. This was in Wiener Neudorf. They use vanadium. Vanadium has multiple oxidation states, so you can use this very nice. And with the color, you can see also which state. Is it the empty state? Is the charged state? So this is a quite interesting story with this battery systems. But again, it doesn't solve the problem because these are real numbers of 2009. Look at this wind energy. This is the park of around Oldenburg for Aeon Transpower Net. Look at these numbers. The numbers are 8,000 megawatt. And now it's much more, by the way, this 2009. 8,000 megawatt is 4 Fukushima reactors coming online and offline within minutes. So this is the situation you have to imagine. And if you just integrate this peak here, just this integral here, this peak shaving of that peak, it's 80 million kilowatt hours in that peak. 80 million kilowatt hours is the world production of batteries on the order, plus minus 10%. The world production of batteries today. So if we are talking about terawatt challenge, I mean, if you want to store terawatt hours with batteries, it will be probably very, very difficult. So what we have, in suggestion of me and many people, of course, take the CO2, take the renewable energies, make a chemistry, and use it as an artificial fuel. This has several names: A fuel, solar powers, solar fuels, A fuels, A to X. We heard today there are many, many names now, but this is nothing else artificial photosynthesis. CO2, because we are here entering the reign of CO2. Because we have a CO2 problem. And this problem, some people still don't understand, and some people even don't accept this problem. And it's very political discussions going on. I want to show you one paper, way beyond any political discussion today, any stupidity, any basically American president's discussion. It was 1896. This is this famous paper of Svante Arrhenius, no less person than a Nobel Prize Swedish Arrhenius. He would have been probably very proud that another Swedish person, a young girl, is stirring up the world much more than these scientific papers we are publishing in this field. Svante Arrhenius, indeed, in this paper, very detailed analyzed what would happen if the CO2 level in the atmosphere increases. At that time, CO2 level was around 300 ppm, and he says it will be 3 degrees, and he also even calculates that in the poles it will be a little warmer than in the, it's really very, very, very nice calculation. And he says if it goes factor 1.5, this is 450 ppm, we will be there in the next summer. 450 ppm we have already soon, and he says 3 degrees. If we have doubling, we have 6 degrees. And doubling is 600 ppm as compared to that time. So if you really never read this paper, read it. And I recommend everyone. So some people say CO2 we can sequester in some deep bedrocks. We had discussed this today also. It doesn't bring anything. I mean, it's just more or less you pump it down and you hope that it stays there. My suggestion, of course, is utilization. You take the CO2 and recycle it to something good. This is the so-called artificial photosynthesis. This was the oldest name for it. Natural photosynthesis is also possible. And interestingly enough, natural photosynthesis is not so efficient. Actually, artificial photosynthesis is much more efficient. Can we do it? Yes. This is another Nobel Prize fellow, George Olah, 1994. He got Nobel Prize for carbocation chemistry. He passed. Also, University of Southern California. He published this book in 2006, Methanol Economy, but in the picture you see this CO2, also this methane, CH4 is in there. He goes for methanol because methanol is liquid. Liquids have always higher energy density. Another important person I have to bring to your attention is Michele Aresta, good friend and esteemed colleague. He's retired from University of Bari. And he has been working since 40 years in CO2 chemistry. For a chemist, CO2 is just a molecule, and it's not a monster, it's not a bad thing, it's just a molecule, and you can make chemistry on it. And this book is really impressive book, Carbon Dioxide as a Chemical Feedstock of Future instead of this petrochemical plants. Can you do with CO2? What can you do with CO2? You can see just an example in the zoo of chemistry you can do with CO2. Yes, photochemical, electrochemical, now biochemical reductions, we can use all of these things. And if you put 8 electrons in the system with CO2, you can get methane. Formic acid is the easiest one. This is only with 2 electrons. This is C1 chemistry. If you studied chemistry, you have seen this before. Can we do that? Yes, we can. Actually, every fuel cell, you can turn around and pump CO2 in there and get methane back. This is the so-called electrolyzer mode of the fuel cells. It's a little bit difficult with the catalysis in this normal fuel cells, high temperature fuel cells, you have to use different catalysts in the reverse version, but inverse fuel cells can be a separate machine. So we created also this company, Solar Fuel, in 2006. This company basically moved to Germany, to ZSW Stuttgart. This is the Konkurrenzveranstaltung, I believe, to ZAE. So it's interesting that they are really big fabrication scale prototypes of this technology was developed. And in a project with Audi Corporation, This is the so-called methanization project from electricity and electrolysis and making hydrogen. By the way, just one remark here. Many people talk for hydrogen economy, but many people don't talk about green hydrogen. They want to make hydrogen from methane. But if you take hydrogen from methane and make again methane, so this is nonsense. If you burn coal and use this energy to recycle the CO2 is nonsense. This is the absolute stupidity you can ever imagine. It will create much more CO2 output. But I'm afraid to say that several industries are now exactly going onto that train because they have smelled money in this hydrogen boom which we have, and they want to strip the hydrogen from methane, from fossil methane, and then sell it to a higher price and basically tell the people, hey, we are making CO2-free energy in hydrogen. So be careful, there are a lot of banana on the street. So you can make this kind of system. So this company which we created moved to Stuttgart, changed the name to E2Gas. They had these huge factories built also, and now the Hitachi took over the E2Gas. So from our point of view, you have seen this diagram today several times in the afternoon. There is no difference to an organic solar cell for me. Just instead of taking these electrons out electrically, you just let them make chemistry. This is electrochemical or photoelectrochemical catalysis. So if you have a good system, stable system, it should be possible to work with donor acceptor systems, let's say in bilayer format, perfectly also with photoredox systems. Can we do this? Yes, this was the thesis of Engelbert Tortenkirchner. He just finished his habilitation in Innsbruck, University of Innsbruck. He used, for example, our famous P3HT with P3HT and this catalyst called pyridinium catalysts. They create methanol, for example. There's an electron transfer, not on C60, but on something swimming in the solution. This is photocatalysis, photoelectrocatalysis. And you can use this rhenium catalyst, for example. Rhenium is a very famous molecule which we call the so-called Jean-Marie Lane catalyst. So if you hear the word Lane catalyst, this is this animal here. Recently, this was Halime Coşkun's thesis. We also took dopamine, guanine, all these things, make polymers out of it with chemical vapor deposition. And you can make these polymers, you can use these polymers to make electrocatalysis, and they work very well, actually. Not so competing with polyplatin, but still an organic catalyst. It's really remarkable efficiency here. So, but the best catalysts in the world are the biocatalysts, and these are called enzymes. I'm educated as a physicist, so I became 26 years ago professor of chemistry, physical chemistry in Austria and Linz. Now, in the last 15 years, I'm getting more and more biologist in the sense I had to learn myself a lot of refreshing biology. So what these enzymes do is enormously selective. So they act only on one reactant and give only one product. This is their unique marketing point. So, however, the bad news, they need chemical food, and this is normally NADH, NADPH, some kind of cofactors, people call it. Can we use that? Yes, we can, but these cofactors are bad news. You see, these three enzymes need 3 more cofactors to create this methanol from CO2. They do it perfectly. However, the NADH is a showstopper. So I basically didn't like this NADH. So can we do it without NADH? Yes, electrochemically we can do it. And my students went even further, and they actually, Stefanie Schlager and Anita Fuchsbauer, they came to me and they said, Professor, we should use bacteria. I said, come on, I don't want a bacteria in the laboratory. I mean, no, but these are good bacteria. These are methanobacteria. They do exactly what you want. They create methane from CO2. And I never thought it will work. It looks ugly. I mean, it's really the utmost a physicist can take. This is bacterial electrochemistry. These electrodes are fully covered with these bacteria. They grow, they are very happy, and they take the electrons from the electrode and create methane. So this paper actually created quite some noise because this is bacterial electrochemistry for CO2 reduction. So we can also use directly enzymes. These are enzyme immobilization. If you are informed about this problem, the biggest problem is how to bring enzymes to the electrode, to lock them to a heterogeneous catalysis purposes. That's called immobilization, and it's a real big problem in the entire biology. So we work with many of these things, again, Stefani's thesis. I don't want to go into detail, but you can see we can create methane, we can create hydrogen, and by just giving electrical energy into biological systems. There is no cofactor here, there is no NADH, there is no basically any kind of carbon source except the CO2. Yeah, this basically is the last thing I want to show. And now coming to the beginning picture, this was a nice collaboration with this Olmutz group in Czech. And Hatay finished also her PhD, went now to Bangkok, back home. So this is an immobilization technique. And this is something really difficult to establish. If you have a graphene sheet, you have to modify the graphene sheet with graphene oxide and graphene fluoride, etc., and then create a chemical anchor so that the biological molecules come and hook on that. By the way, the same problematic of what we call immobilization is the basic problem of nearly all biosensors. All biosensors are based more or less at the end of the day on this problem, how to immobilize the bio agent onto a given electrical or optical or material surface. And this is something really which I like very much because here is the biology, here is the electrochemistry, here is the graphene chemistry, and the graphene chemistry comes from Aristides, and we put all this biological system on top of it. So this academically, it's very interesting. If it will ever make into a large-scale use, I don't know. But I hope that the people will get the idea and people can use this in a larger scale, because biotechnology is well known. I mean, everybody drinks beer, at least I know everybody drinks beer, and beer is a biotechnological process. This is hectoliters of beer are done by bioenzymatic fermentations and all these things. This biotechnology works. I mean, this is not something which is, let's say, out of this world. So generally, our institute is working on these fields here. I didn't talk at all about these bioorganic electronic devices. This is a whole different issue about artificial retina. Retina, for example, is nothing else than organic solar cell. Just working in a biological environment, exciting and opening ion channels. This is just a list, and I mean, if I would list now all the people contributed, and many of you, of course, will be also there. But the point is that I just take a cross section on the last couple of years. I want to mention Siegfried Bauer, my good friend and real collaborator and colleague in Linz. He passed away 2 years ago with cancer, so I really miss him. And I want to mention his name specifically. And many, many visitors, many students, generations contributed to it. I want to acknowledge, of course, this Wittgenstein Prize. Wittgenstein Prize is an honor, of course, to get in Austria. However, on top of the honor, it's money. And it's big money. And it is money where no questions are asked, you know. this is a dream. I wish every one of you, one day you have such a possibility that somebody gives you money and no questions asked. So you can do all these kinds of crazy things. With this, thank you very much.